Hello friends, this is Anand Pai, founder of Academy in Pursuit of Engineering Excellence Apex. Today, we are going to continue our lectures on fluid mechanics. We have started with chapter 1 from the last video. Today is the second part of the chapter 1 and that would be Newton's law of viscosity with the Newton's law of motion. Now let us see. We will recap what has happened in the first video. In the first video, we talked about what is a flow and what is a fluid. Okay. So in the last video, we said flow means continuous deformation under the action of forces. Okay. Now this is not entirely true. Okay. Now continuous deformation is correct. Okay. But when you consider only force, continuous deformation does not happen under the action of normal forces alone, because that is it's equivalent to pressure. Now it will cease at some point of time, okay, because the stresses, the normal stresses which comes will react to the pressure which is put. So normal forces we did not we are not worried. We are worried only about shear forces. So under the action of shear forces there is continuous deformation, and that is called a flow. Now what is a fluid? Fluid is a substance that flows under the action of infinitesimally small shear forces. That means however small the shear force is, there is flow. That is, there is continuous deformation. Now let us go one step further. Okay. Now here we have applied shear forces. Because of the shear force there is continuous deformation. Now the question is, how the force which is applied here is how the force what we have applied here translates into deformation. That is the magnitude of deformation. How fast it deforms. Does all the fluid deforms in the same fashion? Is there some fluid which goes faster, deforms faster, and some fluids deform lower? So what is that which decides the rate of deformation? How fast the deformation happens? What is that which decides it? Okay, or is that all the fluids deform in the same pace? We do not know. Let us see that. Another thing is this. Now what happens to a fluid particle somewhere in between? What is the motion? How does it move? That is another question which we have to have. What is the acceleration it will have? That is the another question. Another question we would like to have is, if the forces is removed, will the deformation cease? Now, if the deformation has to cease, how long it will take? And what is responsible for that? Okay. So let us see that. Okay. So now here Newton's law of motion comes handy here. Now if you have to see, after the removal of forces, how does the fluid particle go? Now we have to understand that if there is no forces acting, then what will happen? It will continue to flow. That is what comes from the Newton's first law, which says that every body continues to be in rest or in uniform motion until and unless acted upon by a force. So this fluid particle, if it is not acted by some other forces, then it will continue. So what is that force? This is one thing we have to answer. Okay. Next. Now when the force is applied, how the acceleration happens? That is the next thing we have to understand. For that we need Newton's second law, which says that rate of change of momentum is directly proportional to the force applied upon a body and is in the direction of the force. Now here rate of change of momentum is dmv by dt, which goes as m. If m is constant, only when the mass is constant you can take out m and you can say m into dv by dt, that goes as ma. So force is equal to mass into acceleration only when mass is constant for the body. If the body accumulates masses, then the Newton's law has to be told in a different fashion. Okay. So now this is what Newton's law is. Now based on third law we are not discussing now. Okay. Based on these two laws, let us see. Yeah, this is one thing which is there. If there is no change in mass of the body, then force is directly proportional to the acceleration. Now the two question which comes. How does the shear forces cause acceleration of the fluid particle? Now the question is, there is forces. When the forces is there, a fluid particle over here, what is the acceleration of that fluid particle? How we can determine that acceleration? That is the first question. Second question, in that only, that means how, in other words, how does fluid particle mass influence motion? This is another similar question. A fluid particle will have a mass. Will it influence? And how, if it influences, how does it influence? Okay, this both of things we have put on the same thing. Yeah, so same question, we have added these two. Second question, once the forces are removed, how long will it take for the fluid element to come to rest? Okay, so once the forces are removed, how long the fluid element which is deforming will stop its deformation? Okay, so how long will it take? These are the two questions we have to answer. So let us move forward. Now let us see Newton's law of viscosity. Newton's law of viscosity states that shear stress in a fluid element is directly proportional to the rate of shear strain. Here what we have to emphasize is the rate of shear strain. Now when we compare this with the solids, in solids shear stress is proportional to shear strain. So in fluids, shear stress is proportional to the rate of shear strain. In case of solids, shear stress is equal to modulus of rigidity into shear strain. The constant of proportionality is modulus of rigidity. Whereas in case of the fluids, the shear stress is equal to coefficient of dynamic viscosity mu into rate of shear strain. So what differentiates solids and fluids is this rate of shear strain. Okay. So now what is this rate of shear strain? We will understand. Now rate of shear strain d gamma by dt is equal to d by dt into tan inverse. If you consider this particular fluid element, it is dd dash by ad, tan inverse of dd dash by ad. This we can write because shear strain is nothing but the angle by which it is deformed. Now when this angle gamma or the shear strain is small, then what we can do is we can write tan theta is equal to theta. Here one thing we have to keep in mind, that this theta has to be in radians, and when you take it as a ratio of two lengths, it is going to come in radians only. So now if tan theta is equal to theta, I can write this as d gamma by dt is equal to d dd dash by ad divided by dt. So now let us continue this. Now this d dash, this thing I am going to write it as delta x, and this AD I am going to write it as delta y, and the small differential of that, when you differentiate this, that is limit delta y tending to 0, what is delta x by delta y? If we see, then it becomes dx by dy. So d gamma by dt is dx by dy by dt. Now if you continue this, d gamma by dt is 1 by dy into dx by dt. Now what is dx by dt? It is the velocity in the x direction, or the component of velocity in the x direction, which is du. So I can write d gamma by dt is equal to du by dy. What does it say? It says that rate of shear strain is actually equal to the velocity gradient. So if you have to find out the rate of shear strain, we can just find out the velocity gradient at that particular point, which is easy to find experimentally. So by doing that, we can find out the rate of shear strain, and we can apply Newton's law of viscosity, saying that the shear stress is equal to mu, the coefficient of dynamic viscosity, into du by dy. Now what happens? This dynamic viscosity, coefficient of dynamic viscosity, is different for different fluids. So what will happen is, for different types of fluids, the shear stress is different. The rate of shear strain is also different based on the force which is applied. We will see all these things now. Okay, we will see how this shear stress causes force, and how it is responsible for the acceleration of the fluid element, or the deformation of the fluid element, and the acceleration of the particle inside the fluid element. Okay, so we will go further. Now let us try to answer the questions we have put. How does the shear forces cause acceleration in the fluid particles, and how does fluid particle mass influence motion? Before going for this, let us see a practical example. An example is like this, where there is an infinitely big plate above which there is a fluid. Above that fluid there is another infinitely big plate which is moving with a velocity V. Now let us see how the fluid particle which is situated here, or a fluid element here, behaves. Now you see here, this difference we are taking at delta y, and at any point the gradient is taken as du by dy. Now this is from experience that in this type of flows the velocity gradient will be like this. Okay, so let us see. Now first of all, shear stress in this any fluid element here being taken is equal to mu into du by dy. Now note that previously when we had taken this, here this delta y is very small. This delta y, that AD, is very small. Only then I can do this. So here d by delta x by delta y is nothing but limit delta y tending to 0 dx by dy. That means this fluid element is almost a point. Okay, so with that particular thing into consideration, here at any point in the sense, this is the point where we are taking the fluid velocities. So this is the velocity, how it is there. At this stationary plate, the velocity is 0, and the fluid continuously goes to this velocity. Now the fluid velocity is equal to the plate velocity only when the fluid sticks to the plate. This is called no slip condition. If the no slip condition is valid, only then this is valid, and we consider that no slip condition is valid in this case. Okay, and now let us see. So tau is equal to mu into du by dy. Now shear stress at any point here in this fluid element is equal to viscosity of this fluid into du by dy. Du by dy is the velocity gradient. Now let us see more. Now here, because of this being applied, the force being applied, it is going with the velocity. So here we can keep velocity as constant or force as constant. So I am keeping the force, because of which on a steady state this is the velocity which it will reach. Now here this F mu, what is there? Now tau I have written as F mu by A. This is not same as the force applied here. This force is the applied force, and the force here, what is it? It is the resisting force because of viscosity. The force coming because of the shear stress. Shear stress is the reactive thing. Okay, so if we apply say pressure, then there will be normal stress. If we apply shear forces, then there will be shear stresses. Okay, so this shear stress, shear force per unit area is the resisting force, not the applied force. Now this I can write it as F mu is equal to A mu into du by dy. Now let us go. Now here you can observe here this one point I want to say, that here this is similar to drag force. Now drag force is the resisting force for something to move. Say aeroplane is moving in a air. So here what is the drag it is experiencing is based on this particular thing. One of the thing, this is called viscous drag also. So now viscous drag on the sphere is equal to Fd is equal to 6 pi mu Rv. Now why did I put it here? Observe here, shear force, sorry, the force, resisting force due to viscosity is proportional to velocity. So here also you see it is proportional to velocity. Generally the resisting force, the viscous force due to friction in fluid. This viscosity is nothing but friction in the fluid. Okay, so this fluid viscosity or fluid friction force is proportional to the velocity. This is a very, very important concept that we have to understand, that drag force or the viscous force is proportional to the drag force due to fluid friction or due to fluid viscosity is proportional to velocity. This will come handy in further chapters. Okay, now F, that is applied force, should be equal to F mu plus Fa. Fa is force which is utilized for acceleration. F mu is the force which is enough to overcome viscosity or viscous stresses. Okay, so here this F is F mu into F. Okay, So now how does shear forces cause acceleration on the fluid particle? Because that shear force will be used in two ways. One is to overcome the viscous forces and to viscous resistance, and then to accelerate. Now this acceleration, this F mu is A into mu into du by dy plus m into ax. Ax is the acceleration in the x direction. So here whatever the force we are applying, it is not just utilized in accelerating, it is also utilized in overcoming the viscous drag. Now if you have to find out what is the acceleration, then we have to go like this. We have to take out acceleration this side, F minus a mu du by dy. That way we can know what is the acceleration, what is caused by the shearing forces which I applied. When I say shear force, I am saying the force which I have applied on this element, okay? Or you say in any cases here in this on this plate, what is the force? That's what we are saying, okay? Now that means F1 is equal to C1. If I say A into du by dy is C1, which varies along this line from here to here. It varies because in this case it doesn't vary, but there are cases where du by dy varies when you go from top to bottom. But now here we are considering fluid particle only, infinitesimally small. So we can do this, okay? Now the mass is considered, the smallest mass will be considered, okay? So now next. Now this is similar to damped vibrations, okay? See, in damped vibrations also you can see mx double dot plus cx dot. C is the damping coefficient. See, always in damped vibration the damping is because of the fluid which is there, and say one of the reasons is fluids, okay? There are internal damping also which happens inside the solid, but sometimes damping happens because of dashpot type of action, okay? And there x dot, see here, it is proportional. The force which is there is the force which is applied has to overcome mass into acceleration. It has to overcome damping coefficient into x dot, which is similar to C1 here, almost similar. And then this is due to spring force, and this is the applied force which is there. So the applied force has to overcome spring force, damping force due to viscosity, and then it will accelerate. This is how the applications we can see. Now let us answer the question number 2. Once the forces are removed, how long will it take for the fluid element to come to rest? Now here this is the equation we are taking, where max is equal to F minus a mu du by dy, which we have taken from this equation. Okay, the equation over here, this is the equation we have taken. Okay, so now next, here once the forces are removed, F, the applied force, is equal to 0. So this is the equation which we get. And here if I bring down m down, mass of the fluid element, this becomes minus a mu by m du by dy. That means here acceleration is reducing. That means it is decelerating. The fluid element is decelerating. And the main reason why it is decelerating is because of the viscosity of the fluid. Now this can be written as du by dt is equal to a mu by m into du by dy. Now to get the time, we have to integrate this. Now integration is quite difficult here, because here u is du by dt, and then here also du by dt, and it is there on both the sides, and also differentiation with respect to time and y here. So this is going to be a bit difficult, okay? So we can do this numerically, but how do we do numerically? We find out u at a small time step afterwards, like starting initial time is there, after that we find it out at the next step. Now how do I do this? I have actually integrated this, okay? When I integrate this, u here, ui plus 1 is equal to this number into delta t plus the initial u, okay? So when this is done, okay, we can see here, okay, we can do this. Now here velocity of the element u is ui when the force is removed at t is equal to 0. Now, this t is equal to 0 we can continuously set and we can get the answers. Like, now we will see what is the velocity at this moment of time, and say after 0.1 second what is the velocity. Next, this 0.1 second will be the 0, at the velocity at 0.1 second will be the initial velocity. And then we will see what is the velocity at 0.2 seconds. Like this we will go until the velocity becomes 0. And this is how we can find out what is the time it takes for the fluid element to come to rest. Now here, in case of Couette flow, that is what we have considered till now. For the Couette flow, what happens is, this du by dy becomes quite easy. It becomes ui, which is v, divided by delta y. That itself becomes the velocity gradient. Now, by doing this iteratively, might be we can do a computer program for this. We can find out what is the time taken. We have to add up all the times and we have to find out what is the time taken for u to become 0. Step by step procedure. So this is how the things can be done. Now let us summarize whatever we have studied till now. First one, for a point in a fluid, shear stress is proportional to the rate of shear strain. This is Newton's law of viscosity. Second one, rate of shear strain at a point is equal to the velocity gradient. Drag force due to viscosity is proportional to the velocity of the fluid element. Applied force on a fluid element is utilized to overcome viscous force as well as to accelerate the fluid element. The time taken for a fluid particle to come to rest is proportional to the viscosity of the fluid. I hope you have understood whatever we have discussed. If you have any further queries, you can comment on this video, as well as if you have any further suggestions, you can give me. Also, don't forget to subscribe the channel as well as click the bell icon so that you can get notification about the further videos. Thank you very much. Best of luck.